All right, so we're all in agreement that Spider-Man's terrible, Bronny is like 10 times better than LeBron, and country music is the best genre of music to ever exist. Cool. Awesome. All right, so today we get to start 1.7. And our focus in 1.7 is writing proofs. Proofs.
I think Eli told me about this. He said it was hard.
It's not hard. Don't believe them. How about you decide for yourself?
Okay.
Cool. Remember, here's the thing. We are going to start writing proofs today. There is not going to be a chapter following this where we don't write proof. Like, it's going to happen all year long. The thing that I want everybody to be real clear of, some of you guys will immediately get it, and by the end of next week, you'll be comfortable with it, and you won't shy away from writing them ever. Some people will not feel comfortable with writing proofs up until like March or April. And honestly, I hope it's not the case, but realistically, somebody in here will get to the end of the year, and maybe more than one, who knows, and you're not going to be able to write good proof. Okay, your ability to write a proof does not determine whether you do well or poorly in this class. It determines whether you get 1 or 2 points on questions on quizzes. Okay, now as we go through here, you are going to be able to write a proof, at least a basic proof, here in just a few minutes, and we're going to jump right in. First off, we're going to talk about a few little pieces, and right off the bat, I want to define for ourselves a theorem. Now, you guys have seen the word theorem before, I think, and I can think of one theorem that everybody knows. The Pythagorean theorem. Now, anybody ever heard that diamonds are forever? Like, it's a pretty big push in like advertising for like jewelry stores. Diamonds are forever. Diamonds are super valuable, if you guys didn't know that. But I don't think there's really any value to a diamond being on your finger. What are diamonds actually valuable for?
Their hardness.
They're hard. They are on the hardness scale. It is a 10 out of 10. There's not harder than a diamond. You cannot scratch a diamond with another anything. Now there might be a few like alloys out there that can do it, but naturally nothing will ever scratch a diamond, but a diamond will scratch everything. Okay, they are extremely hard. Why would anybody in human culture care that we have a mineral or a rock, a crystal if you'd rather, that is extremely hard compared to everything else?
You can make good tools out of it?
You can make tools out of it. Where would you possibly need a really
Pickaxe.
hard tool?
Like
Drill bit.
What the heck?
I don't drive to school because I live right there, but I assume a lot of you guys do. If you want to drive, you use oil, I would guess. Like you use petroleum. It's either diesel or gasoline. I don't think anybody here drives a Tesla. Even if you did, you're still using petroleum to get your electricity for that. If you drill into something, anybody ever done much drilling or woodwork at all?
Yeah.
You ever drilled in a screw or removed a screw and then went to grab it and it burned the hell out of you?
Yeah.
Okay, they get hot. What do metals do when they get really hot?
No.
They melt. And could you possibly drill a good hole with a liquid drill bit because it got so hot?
No.
No. If you want to drill deep into the earth to get these valuable resources, use diamond coated stuff. Like that's where the real value of diamonds is. I don't think that's personally, and I'm just going to teach your hat off. You use diamonds to get diamonds, absolutely. The first diamonds, you can find them without going super deep, but in big mines you have to start deep. Okay, teach your hat off. I think that diamonds serve no real value in the jewelry sense. I do not own a single diamond that has been mined out of the ground, and I would never suggest that somebody buys one. I think it's like, again, teach your hat off, right? This is just my opinion. I think that diamonds, if you're going to buy a diamond, buy a lab created one. One, they're way cheaper, and two, people didn't like literally get forced into slavery to dig these things up out of the ground somewhere. Like it or not, a lot of diamonds around our world, and even if they're certified, it's not always the case, they come from maybe not so great of business practices. Cool. You should buy diamonds, but they should be lab made, not naturally out of the ground that somebody was like not in a good situation. Okay, with that said, diamonds aren't forever, just so you guys know. Eventually they will wear down over time, like the universe is going to exist for a long time. Eventually, diamonds will be gone. But you know what won't be gone? Theorems. Theorems are really and truly forever. Now, when we're looking at this, like it sounds like a joke, but I don't think I'm kidding. But the philosophical part of it, I don't really care where you stand. A theorem, by definition, is a conjecture, which is like our fancy math word for a guess at a pattern or something. But it is a conjecture that is proven, or that has been proven true. Okay, when we say it has been proven true, What this means is if we have something that we write, this is called a theorem, nobody will ever be able to find a counterexample against it. It does not exist. The Pythagorean theorem is true for every single right triangle that will ever exist in a two-dimensional space, which means long after humankind is gone, the Pythagorean theorem will still be true. Even though there's nobody to say it's true, it will still be true. Was it true before, like, even though nobody had said it, was that same concept true before it was discovered? Yes, it was always true. It always will be true until the universe doesn't exist anymore. Now, there's a bit of philosophy on that, so you can pick whether or not you truly believe that. But we have theorems in here. Now, when we write a theorem, it is not just a conjecture. It is something that we will prove. In here, our proof will always follow the same format. I'm going to make a comment. Proof in here, our proof, will always, 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 and I'm going to make that a capital always just to indicate how important this is. Our proof will always be 2 columns. Why I specify this is because in any geometry book that you ever look at, like even as I'm looking at the homework, I see on number 18 it says write a paragraph proof. Nope. That's what it says. That's not what I want you to do. I don't want you to write paragraph proofs. I want you to write what sort of proof?
2 column?
2 column. You might not even know what that means yet, but you're going to write 2 column proofs all the time. Okay. Yep, you literally just use 2 columns. We don't have to write sentences, and I'll show you. We'll do 1 or 2 or 3 together today, and I'll let you guys try. Every proof that we do will be 2 column. Higher level math, it makes sense to use paragraph proofs, but I don't want to have to try to make sense of your paragraphs and your math logic written in Word. Let's just do it 2 column all the time. Okay, for these, a little bit more with it. First column is the statement that we make, and it'll vary depending on the proof. First column is statement. Second column is justification. Now, you will get practiced with how we justify these things, and it depends on what we're talking about as to what specific justification we'll use, but that's it. Okay, theorems, proven true. We're going to get a lot of theorems in geometry, and here's the thing. There's so many that there's going to be some, and I guarantee there are some that I don't remember exactly how it works, because legitimately I think we'll probably have like 100 of them this year. Okay, anytime that we get a theorem, what do you think we have the opportunity to do?
Solve.
Prove. We get a chance to prove this theorem and not just accept what your authors are saying is something is true, but we're actually going to verify that it is true, and it's always true, and it always will be. Now, for proof, and we have one, I know I said we're not going to do a ton more writing. There's always going to be writing for our notes. Your homework will not be big wordy sentences again, though. Okay, let's get one last definition, and then we'll jump in. A proof, by definition, is a deductive argument, which means we get to use rules and things like that. A deductive argument, logically moving, uh-oh, is this 2 L's?
Yeah.
Okay. If it's not, I don't know. Deductive argument, logically moving from, what do you call the first part of a conditional statement?
P.
So it's P, it's the hypothesis, to the, to Q. Hypothesis, to, what does Q represent? The conclusion. Okay. Our job is going to be to start at our hypothesis and then show logically that the only natural thing that we can wind up at is going to be whatever conclusion they're claiming. Every single time. Now, I'm kind of crazy when it comes to how we write stuff down. Proofs can get really ugly and disorganized if we let them. But if we all agree to follow a certain convention, I don't think that they'll get ugly and disorganized. When we write our proofs, and I guess I'll do it here. Don't write what's in bright pink, okay? Or lilac or whatever color this is. When we write a proof, we're going to have 2 columns, always. We'll have a statement, and I'm not going to label these right now. We will in our proof. Again, don't write this yet. Here's what we're going to wind up doing. I'm going to start with A, and I'm going to write some statement here. And then I'm going to come over here, and I'm going to justify why am I allowed to write that statement. Okay, that's always how we're going to start. Now, what I don't want to happen is if you use several lines here, like let's say for some reason you wrote 3 lines of stuff on your first part. If I write B here and B here, do you guys agree it's going to get off track a little bit? I want you to try very, very hard when we're writing these. Let's keep these like this. And like I'll demonstrate this. Yes? How much money do you have in your pocket? How much money do you have? Okay. I don't know that she knows I was kidding. Yeah. All right. I hope she knows I was kidding. Does she know I was kidding? You'll tell her I was kidding. Okay. Cool. This is not a pay to use the bathroom school, just so we're all clear. All right. Should we do a proof?
Yes.
Well, if we're going to prove something, we need something to prove, right? So here we go.
Oh, when you're doing this, do you just make a statement about anything, or?
I mean, hopefully related to what we're proving. Let's do an example. Like, that was me messing with you, right? Let's do one and see if you start that question. Okay, so check it out. 4 theorems when we get them. And we're going to get our first theorem. Have we even had a bullet point yet? Theorem. Yep. Okay, your book will have a lot of them. I will henceforth only write THM. That is my shorthand for what word? Theorem. Now, some theorems get names. And I'll use a tilde since we're within this theorem section. Okay, this in your book, and I'm glad they do it because I do it this way. We are about to see theorem 1.1. We are not in section 1.1 of your book. We are in section 1.7. Okay. Theorem 1.1 simply tells me it's in chapter 1. That's the 1 part to begin with. And how many other theorems have we done in chapter 1? We haven't done any yet. This is the first one. Chapter number of the theorem. So, sometimes they will have names, and we actually do get a name for this one. We're going to look at the vertical angle theorem. For those of you that used vertical angle on your quiz, and I didn't give you points, you're about to see what it really is, even if you didn't know what you're writing down. Okay. We have our very first theorem, and it's called the vertical angle theorem. We will use a vocab while writing this proof, but I'm not going to really define it because we're going to be able to make sense of it just from what the word is, but we'll make sure it's clearly a vocab word, and we'll talk about it, but I don't think we need a formal vocab like definition. So here we go. Here's our theorem. Theorem 1.1, the vertical angle theorem, simply says vertical angles are congruent. And notice, I'm going to use shorthand all the time. You should get used to using the real ones. I will try to avoid the Holloway-isms, but real shorthands that exist, we should use them like consistently. Okay, there is a natural question that's going to arrive in this. What's a vertical angle? Not, I mean, we'll get here. We do want to prove this, but we don't have any idea what we're proving yet, I don't think. It's kind of old school now. Do you guys know who Des Bryant is?
Des Bryant? I've heard that.
Okay, so there's a Cowboys reference, but it's too old now. Check it out. I'm going to throw up an X here. And I'm just holding an X up on the board, right? We'll draw in a second. I have how many angles up on here?
4.
So there might be more than 4 if you want to get really specific. But we all agree that there's 4 angles here.
Yeah.
If I said vertical, this top angle here is vertical to which angle? Right here. They're straight across from each other. They're formed by 2 lines intersecting. This is a vertical angle. Now, I'm going to draw 2 intersecting lines on the board. I'm going to leave this blank for, nope, I'll just draw it right here. So here's what this theorem looks like if we do it like this. Here's a line, and here's a line. They could be segments, they could be rays, it doesn't matter. Do we still see these same 4 angles?
Yes.
Is it those 4 that you saw? Yeah. So here's my first question. Without having to like make a big definition, what angle is vertical to angle 1? 3. They are formed, they share a vertex, and they're across from each other. For those of you that answered vertical angles on the quiz, you were correct, but if you couldn't tell me what it was, it didn't give me the points. Is there another pair of vertical angles?
4, 2.
Even though they're horizontal, they're still vertical. They just have to be across from each other in this situation. Everybody cool with that?
Yes.
Straight across, sharing a vertex. So angles 2 and 4 are vertical from one another, and angles 1 and 3 are vertical from one another. We have 2 pairs of vertical angles here. Okay, here's my first challenge. This theorem claims that 2 should be congruent to what? 4 vertical angles. 2 and 4 should be congruent, and 1 and 3 should be congruent. Here's my first challenge, and I'm going to give you guys 60 seconds or so. I want you to talk about it. Normally, because we start with hypothesis and end at the conclusion, we want to be able to really clearly identify those. I want you guys to take this statement and write it as an if-then. Vertical angles are congruent can be written as an if-then statement. I want you to try to write this with your neighbors. You can talk it out. We'll come together. Write that as an if-then statement. Here we are. Who feels confident that you can write this as an if-then statement? Ronaldo, what do you got?
If angles are vertical, then they are congruent.
Did anybody else come up with the same thing? Love it. If angles are vertical, then they are congruent. Okay, it doesn't have to be word for word, and I got a really good question. Can I switch this around? Can I say if angles are congruent, then they're vertical? No. Remember, the conditional statement is logically the same or has the same truth value as the contrapositive. That would be the converse. We can't always do that. In fact, this one doesn't work because I can counterexample it really easy. If I said this is a 45-degree angle, are you good with it?
Yeah.
Now, I'm going to just pretend like it is, and then we'll say it's still there, and here's a 45-degree angle. They were both congruent, right? But were they vertical?
No.
No, they didn't share a side, like a vertex. Nothing existed there. Okay. So I promise not every proof will take this long. I'm just trying to really demonstrate that they're not terrible and they're always going to follow the same. Can you tell me the hypothesis here? Angles are vertical. What's the conclusion that we need to wind up at? Okay, so let's do it. We're going to write our very first proof right now. Cool. Nope, we have not written the proof yet. Okay. I'm making you guys do a bunch more than you normally would. I would typically just give you this statement and say, let's prove it. But we're building up to it. Okay, here's the deal. Ears wide open. We will always assume that the hypothesis is true. And if we can go from a true hypothesis and end with our final conclusion, that's a proof. We just need the logical step from angles are vertical and wind up with they are congruent. So, when we do this, there is always going to be the same first step every single time, no matter what. When we write our proofs, we're going to start with these angles are vertical, and we're going to end with somehow logically that they are congruent to each other. So let's do it. Right off the bat, on statement A, I don't care which one we use, but we need to show that vertical angles are congruent. Are we using 1 and 3?
Yeah.
Are we trying to get to 1 and 3 or 2 and 4?
1 and 3.
It doesn't matter which one we go with. 1 and 3 seem fine to me. Because I know that these will be congruent, but so will these. Okay, check it out. Our first statement, if we all agree that we're going to use angles 1 and 3, let's just write our hypothesis in this form. Angles 1 and angle 3 are what sort of angles? Not yet. We can't jump right to the end. Vertical. Now, I'm going to sneak this in as a cap, just so we can kind of say, look, there is our vocab. Vertical angles, they always get formed by lines crossing. Okay. Every proof will always start with your given, or your assumption, your if part, your hypothesis. Our justification for our first part will always be given. You are given some information, and we need to logically show that if you start here with 2 vertical angles, we're going to wind up with them being congruent. Now, there are a bunch of issues that people naturally run into. I don't think it's going to happen on this specific proof, but we want to avoid circular logic. And all I mean by that is we can't say vertical angles, we can't just say that they're congruent because they're vertical, because then you would say, well they're vertical and now they're congruent, which means they're, like, we just go with circles, right? It'd be like if I asked Chelsea to borrow me $50 and I gave her a $50 bill and asked her to borrow me $50. That's dumb. Nobody would do that, right? I would just keep the $50 myself. You didn't catch that, that's okay. All right, here's our first statement. Now, I use language, and I guess I'm not even going to introduce it now. I know that angles 1 and 3 are vertical. I need to be able to show that they are congruent. And I'm going to just push here real quick, and I'm going to force our hand. If I wanted to add up angle 1 and angle 4, and I'm going to ask you guys to finish this for me in a second, and I'm just looking at my picture. I could change the letters. It doesn't matter. What do we get if we do measure of angle 1 plus the measure of angle 4 on our picture? Which it doesn't matter how that picture is drawn as long as they're vertical like this. So they are adjacent, but that's not a number. Can you tell me what number they must equal?
5.
So 1 plus 4 is 5, absolutely. But what about the measures of those angles? That's some degree plus some degree. I do agree with you, but that's not what I'm after. Do we agree that when I put angle 1 and angle 4 together, they form a straight line?
Yes.
Okay, now we're checking your middle school knowledge. How many degrees in a straight line? Do you guys remember ever seeing straight lines are 180 degrees? It's half a circle, right? If I started here and went here, it's half a circle, it's 180 degrees. Okay, so for this is a true statement. Okay, I will never write anything that I'm not certain is true here. Okay, why am I allowed to write this? Like, I need some sort of justification that allows me to do it. And you don't have it yet, but you will. We have a pair of angles, these two, that when I add them together, they form a straight line. Do you guys agree with that? And we all remember from 6, 7, 8, somewhere in there, that straight lines have 180 degrees. Yeah, not trying to make the joke, but do you guys, like, for real all remember seeing that at some point? Okay, so check it out. We have a pair of angles that form a line. I'm going to sneak in a vocab without having to formally write a vocab word, just like we did with vertical. I'm going to justify this by saying these are a linear pair. It is a pair of angles that form a line. It's a linear pair. They will always, always, always add up to 180 every time. Now, you'll get used to this as we do it, but notice, I started with 1 and 3, and now I'm trying to work in measure of angle 1 in my proof. I'm trying to get measure or angle 1 and 3, right? Have I written angle 3 anywhere else yet, though? So here's our first little thing that's a Holloway style thing that I would strongly recommend. I've got measure of angle 1 in my proof. Cool. I need measure of angle 3 in it. Could I also say something about the measure of angle 3 plus the measure of angle 4? Now I could do it here as well. There's a very particular reason I'm going to do this exact same one. If you were to add up the measure of angle 3 plus the measure of angle 4, what would you get?
7.
So don't just add up the numbers. 180 degrees. Does it also form a straight line?
Yeah.
And I know that they are a pair that form a straight line. It's a linear pair again, right? Okay, don't write this yet. I just want to show you something. If it's pink, just hold off. Okay, some teachers, some texts will physically make you write this all again, and then you would have to justify again. You would say another linear pair. I don't think we need to. If we're going to use the exact same justification, another linear pair, I'm not going to write C here. I'm just going to write the second part using that same justification. So what I'm going to claim is that, well, the measure of angle 3 plus the measure of angle 4 is also equal to how many degrees? 180 degrees. Is anybody adamantly opposed to me just kind of writing on the statement B rather than rewriting another justification? Everybody cool with using just one justification 2 times? Okay. Nothing crazy yet. Notice, and I just want to emphasize, and it takes practice, I now have angle 1 in my proof, but I also have angle 3 in my proof. Now, I need to link these together somehow because I better wind up with angles 1 and 3 are congruent. That's the very last thing that I'm going to write in my proof. Now, we need to rely on some old algebra ideas. If I ask you guys to evaluate, and I keep trying to write on the board, but I'll do it here so that anybody who's gone can see it. Remember, if it's pink, it's just to think, right? Okay. If I have this, x equals 7, find, don't write it, just think it, 3x plus 1. Can you guys find me 3x plus 1?
Yes.
Is it 22?
Yeah.
How on earth did you possibly do that? You plugged it in, right? If I just wanted to change the word, could we say and agree that I just substituted in for x? Because I know what x is equal to. Okay. What are both of these things on the proof again equal to? So if and I really wish everybody was here so I could just point to the board because it makes more sense. Do you agree that one measure of angle 1 plus a measure of angle 4 is one way I could write 180 degrees? Is there another way that we know we can also write 180 degrees? 3 plus 4, right? So here's what I'm measure of angle 3 plus a measure of angle 4. When we're looking at this, here's my thought then. I know that the measure of angle 1 plus the measure of angle 4, instead of writing equals 180, what else could I write instead of 180?
360.
They can't write 360. So I know it's 180, right? And here's another way to write 180. So it's probably unnatural here. We're going to try it. Okay. I think that this is a true statement. And in fact, I know it is. And you can trust that I know and you're about to know. And once we get a little practice, you'll feel better about it. If they're both 180, then these things have to be equal, right? Everybody cool with that basic idea? Cool. All right. What did we just do? I'm not going to say plugged in. There was a better word. We used substitution. So here's my justification. If we know something equals some expression or whatever the case might be, I'm going to write substitution. Here's what I would suggest. Here's my shorthand for substitution. Jonah, quick question. If this is my shorthand for substitution, why do you think I advise against using just sub? Prime's got it. Say it again. You might confuse this with subtraction if I just write sub. I don't care if you actually write substitution. I don't want to. I would stop here. Subst is what tells me it's substitution. I'm going to write the whole word. Okay. We're close. What I'm trying to show that these angles are congruent, right? Measure of angle 1, or angle 1 should be congruent to angle 3 in the end. We don't have it yet. As I look at that expression, if I only want it to be angles 1 and 3, is there anything algebra that you've ever done that would allow me to make it somehow get rid of something in this expression? So all I have is measure of angle 1 and the measure of angle 3. Could I subtract something from both sides, as long as I subtract the same thing from both sides?
Yeah.
If we look at the board, what could I subtract from both sides there? Measure of angle 4 is on both of them, right?
Yeah.
I can subtract it from both sides. I'm allowed to do that. That is one of the properties of equality. So I'm not going to show that like minusing happening, but I will justify it. From this line, I think I can arrive at the measure of angle 1 equals the measure of angle 3. Now, you'll notice we're not showing some of the work because it makes it cluttered and ugly. But if I want to really make sure that I can see what happened, or somebody else could pick it up and know what happened, what did we just do? No, we did cross them out, but there was a word that we'd used. So we didn't cancel anything. We used what property? Okay, so here's the deal. You do not have to write anything other than sub, and my shorthand is this, S-U-B-T-R. That's how I differentiate between substitution and subtraction. I'm going to write the real thing. You don't have to write it all. It is really the subtraction property of equality. Now, I don't think we have to be quite this wordy because we all know that if you have an equation, I can subtract the same thing from both sides. That is a property of equality. I'm cool with just calling it subtraction. Are we where? Weird. Are we at the point that we needed to wind up at? Not quite. What was our hypothesis, or what was our final conclusion supposed to be? If the angles are vertical, then what? Okay. If the angles are vertical, then they are congruent. Did I have a statement there that said they're congruent? So careful. Did I literally write angle 1 is congruent to angle 2? That's what I mean. Or angle 3, sorry.
Yes.
No, I wrote their measures are equal. But what does it mean if the measure of two angles are equal? Like,
180.
not necessarily. They're the same. Give me a mathy word for that. Give me a better mathy word for that. The measures are equal means the angles are congruent. That literally means congruent. So check it out. And I know it feels tedious. Sometimes it is, and hopefully won't feel this tedious every time. I know that if measures are equal, then angles are congruent. Okay, check it out. I want to ask, and I don't want to have to write it, what do you think this is short for? Define is a good thought. Not quite, you're close. Definition. Right now, this very last little part, all we have done is use the definition of what? To go from equal measure to congruent. That's must be the definition of what? Congruence. And I'm just going to use a symbol. Okay. This one. We talked a lot more about than we normally will. Like, we'll always work through them, but I just want to really show you what happened. It didn't matter which ones we started with. We started with the assumption that these were vertical angles. Okay, I know that straight lines add up to 180, and that happened twice. I know that I can substitute something in, I can subtract, and all of a sudden we wound up exactly at what this theorem claimed. We didn't cheat at all. Everything that we wrote was justified and allowed in the rules of mathematics. When you write a proof, give me just a second, Klein. Last little thing that you need to include. We always start with the given, end with the final conclusion. You get one of two marks. You can indicate that you are done with a proof using this symbol. Okay, it's just a filled-in box. Now, I have here a fancy book. It's not really that fancy of a book, but it's a really old book, and it was from my college years. And I just want to show you here, I'm going to open to some random page so I can find a theorem, and we're going to look at their proof of it. And I lied. I'm not going to confuse you guys with it. Okay, this indicates that we're done with the proof. Or, and this is purely a style choice, you will oftentimes see QED at the end. One of these two symbols. Okay, QED is not the one that I'll normally write, but lots of books use this. This is Latin for quod erat demonstrandum. Okay, because formal science and mathematics was done for so long in Latin, we'll get a lot of Latin pieces left over. I prefer the box, but if you want to end every proof with QED, you can. Quod erat demonstrandum literally means that which was to be demonstrated. We just demonstrated that theorem. We showed it was always true no matter what. From this point on, it means that if we see vertical angles, guaranteed we can use the fact that they are going to be what? Good, louder. Congruent. If angles are vertical, then they're congruent. That is now forevermore a true statement that we can use. Now, looking at this, feels okay, feels awful. Where would you put it? Okay, that's fair. Does this feel like the hardest thing you've ever seen in all of your mathematics? I hope not. Some of you might, but I hope not. Okay, let's try one more here. Looking at this, if you want, here's our original picture, right? Okay, when we make sense of theorems, sometimes we'll give this if-then statement. I'm going to add one more little piece. As long as you guys have the picture, we can add something. If you give me vertical angles, which do I have vertical angles here? Yeah. This, according to the theorem, if we just want the picture version, implies, and this is not the proof, this is just us making sense of the theorem. If I give you this picture, angle 1 guaranteed is congruent to what?
3.
Angle 3. And what else did you learn?
Angle 4 is congruent to angle 2.
This is the example of how our theorem works. This is the formal proof of our theorem. Now, I didn't use it here. The shorthand that I use for, look, here's our proof, is I typically just use PF. I'm sorry? I think you ask why is there so much proof? Because if we could just willy-nilly use any statement that we want and act like it's true, mathematics doesn't build on itself, ever. We need to be rigorous and make sure that what we're saying is true is without a doubt true. And again, the importance here, how long has it been true that vertical angles are congruent? Since the beginning of time. Maybe even before then, but I don't even know what that means to even talk about before time, because before is a time word. How long will this be true? Forever, until the end of the universe, or whatever happens at the end of the universe. I don't know. I haven't been there. I don't think. Cool. Seem reasonable? Maybe. We're going to get a lot of practice. Okay. We have 6 minutes. Here's what I'd like to suggest. I want to spend all of Monday practicing proof. Okay. Either using a theorem that we see or practicing just the basics of writing proofs. Looking at your sections, like upcoming pieces, there are 6 theorems this chapter. And specifically, there are 6 theorems this section. I guarantee we will approve every single one of them on Monday. Okay, that's not a threat. It takes practice to get good at this. My hope is, even if you're somebody who can never write your own proof perfectly, which it will happen, unfortunately, if you can follow the logic of a proof, I feel like you're like 90% of the way there for what I need you to be able to do. Cool. So for 6 minutes, what do you want to knock out? We used Feelings Friday in my 5th hour class. Would you like to do a basic, quick one in 5 minutes? Okay. So Feelings Friday is something that I do not every single Friday.